The goal of this video is to define potential energy in terms of work, specifically that done by gravity, and see how potential energy is related to kinetic energy. If an object falls from a height of ya to yb, gravity performed work equal to the force of gravity times that displacement. You will have noticed the work done by gravity always works out to be mgh, where h is the vertical displacement of the mass. According to the work-energy theorem, this work done is also equal to a change in kinetic energy of the object. Since the energy change from work done by gravity will always be equal to mgh, it is greatly convenient to reverse our description of the term mgh to reflect the potential of the object to perform work. We then call the term mgh gravitational potential energy, because it reflects the work that can be done by gravity on the object. Potential energy is generally abbreviated with a capital U, and the work done by gravity then reflects a change of gravitational potential energy. To help see the usefulness of this description, think of defining a certain elevation as a height of 0. In this case, let's choose the ground as height equals 0. We then call the potential energy of the mass at any given height mgh, where h is the height above the ground. A mass at height h1 has potential energy mgh1, and a mass at height 2 has potential energy equal to mgh2. So the work done by gravity in the mass falling from h1 to h2 is mgh2 minus mgh1. Notice the work done by gravity is positive because the force and displacement are in the same direction, but the change of potential energy is negative because h2 is smaller than h1. This relationship makes sense if we think carefully about what potential energy is. Potential energy describes how much work the mass could do to another object, perhaps a small nail in the ground. If the object does some work, or if it is released from a lower height, the object has less potential energy available to convert into work done. Remember that by the work-energy theorem, work is also equal to a positive change of kinetic energy. So as objects fall, potential energy is lost, but kinetic energy is gained. Consider the object falling from h1 to h2. The change of potential energy is mgh2 minus mgh1. The change of kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared, and these changes are opposite to each other. Distributing in the minus sign and rearranging the equation so that all of the terms are positive results in a grouping with all of the terms describing the energy at height 1 on the left and height 2 on the right. That is, the sum of potential and kinetic energy at height 1 is equal to the sum of potential and kinetic energy at height 2. The sum of potential and kinetic energy is the total energy, which we'll call E. Then we can say that the total energy at height 1 is the same as the total energy at height 2. This is called the conservation of energy, and is one of the most fundamental principles in science. Consider a mass placed on 4 different slides. We will ignore all friction and air resistance for now. If each mass is released from the same height, which one will be moving fastest when it strikes the ground? If we call the bottom of each ramp y equals 0, and the top y equals h, then the potential energy will change from mgh to 0. As the block loses potential energy, it will gain kinetic energy, so each block will change from 0 kinetic energy to a kinetic energy of 1/2 mv squared. So conservation of energy tells us that regardless of the path chosen, in the absence of friction and air resistance, each mass will achieve the same speed as if they had all been dropped straight down. There's one more vitally important point about potential energy. Notice that kinetic energy, 1/2 mv squared, will always be a positive number. Mass is always positive, and the velocity, which might be negative, is squared. Negative kinetic energy makes no sense. But for potential energy, y, or h, could very well be negative, making the potential energy negative. We are always free to choose any position as y equals 0. It could be well below an object we are considering, or well above. In each case, the object has a different amount of potential energy, but the tendency to change potential energy will always be the same. In either case, the force of gravity acts downward, in the negative y direction. Therefore, Although it is okay to have negative potential energy, the important point is how potential energy changes. In every case, objects always tend to move in the direction that decreases their potential energy.